Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to sensors and transducers, and we will extend our discussion on liquid level measurement using mechanical transducers. Previously we discussed bellows. In this video we are going to discuss the same thing using Bourdon tube pressure gauge. Okay, so Bourdon tube we have discussed previously, so a quick recap. So a Bourdon tube is again a mechanical transducer, a primary mechanical transducer. It means that the output that we get is non-electrical, it's mechanical movement, displacement. Okay, so again we have to use a secondary electrical transducers, and the basic operating principle is it converts pressure difference, again internal and external pressure difference, to the point where it is connected, into linear displacement, that is linear movement, or angular movement. Okay, so pressure into displacement. Again, that displacement can be converted into electrical signal using LVDT, using capacitive transducers, using potentiometer, resistive transducers, or inductive transducers. There are various arrangements. There are various types of Bourdon tubes of different shape and size, but particularly the C-type or C-shaped Bourdon tube is the most commonly used Bourdon tube, which is something like this. So it is made of, again, like bellows, it has to be flexible, so it is made of special flexible metallic alloys, plastic, rubber, which are specifically designed for that particular purpose. So here one end of this C-shaped tube is fixed on a rigid base. This point is connected to the source of pressure which is to be measured. In this case, the liquid level column. This is connected to the source of pressure. Okay. So here there are certain things that have to be taken care of. So it's a thin walled tube, okay, so that it allows movement, flexibility of the free end, and it is bent into a circular arc, the C-shaped circular arc, and the central angle, that is the angle which this makes with the initial angle, okay, this A, the initial angle, this is the initial position where the Bourdon tube is free and it is undisturbed. This angle A, which this free end makes with the fixed end, that ranges from 200 to 270 degree, which allows total movement of the free end, and the closed end, the other end of the tube, that is closed and sealed, and that is free to move, this end, okay, which is free to move. This is the fixed, this is the free end. The fixed end is open to the source of pressure, it is connected to the source of pressure. The free end is closed, it is tightly packed so that it does not allow the pressure to escape, and it undergoes linear or angular movement. Okay, so what happens is that when this fixed end is connected to the source of pressure, because of the difference between the external and internal pressure, this C-shaped free end which is connected to the rigid base, here there is some space between the C-shaped tube and the connecting point, which allows movement of this blue portion, okay, this blue portion, C-shaped portion, it undergoes movement, okay, it undergoes rotation. As a result, we have a pointer or any rod kind of arrangement is connected to that. This can be connected to a pointer scale arrangement, which is the most common thing, or we can connect it to any secondary electrical transducer. In this case, we have an LVDT which connects the free end, and it undergoes linear movement which produces a voltage signal. Same can be done with potentiometer, it can be done with capacitive transducers, it can be connected with inductive transducers, like that. So the mathematical relationship between the displacement of the free end and the differential pressure is given by this relationship. So this equation can be a bit complicated, a bit tricky, but try to understand this. Here the important thing to note here is first the angle A. Okay, this is the initial position of the Bourdon tube where no pressure is applied. Angle A is the angle which the free end makes this with the fixed end. This line drawn here, this is the angle A, the initial resting angle kind of thing. Then when pressure is applied, this free end, it moves to this position, okay, because it's flexible and it moves because of the pressure difference between the inside and the outside. It tries to expand, it can respond to the pressure difference. So at this position, the angle with the fixed end, this line, that is the angle B. So angle A and angle B, and angle C is this movement, okay, with respect to this horizontal line and the line drawn from the free end to the center, that is the angle C. Okay, CAB. Then R is the initial, the arc, the C-shaped arc, which is the radius of that arc, that is R. Okay, and this is the displacement of the free end. So the relationship is C by A. You have in your mind the angles C by A is equal to delta P, which is the pressure difference between the inside and the outside, the differential pressure, into 1 minus mu square, where mu is the Poisson's ratio, E is the Young's modulus of elasticity, then B is the semi-minor axis of the tube, then we have T, which is the thickness of the tube, R, capital R square, where capital R is the radius of the arc, the initial radius of the arc here, R, and then this is 1, then 1 minus B square by A square, where A is the semi-major axis of the tube, okay, the semi-major axis and the semi-minor axis of the tube. This is the tube, this cross section, semi-major axis and semi-minor axis. 1 minus B square by A square, and then into alpha by beta plus zeta, okay, where alpha, beta and zeta, they are dimensional constants depending upon, alpha and beta are dimensional constants, while zeta, which is equal to RT by A square, that is also a dimensionless constant. Alpha and beta, they depend upon the material which is selected for the design of the Bourdon tube, and A, B, C angles, they are the angles which I mentioned in the beginning. Okay, so this is the relationship. Then from this we get the radial displacement, because the displacement has two components, radial and tangential. The radial one is given by C by A into R minus 1 minus cos A, and tangential component is given by C by A sorry, R into A minus cos A, and the total displacement, that is equal to root over of y radian square, that is the radial component square, plus the tangential component square, the sum of these two. Okay, okay, this is the basic principle of Bourdon tube. Now again, here we are using this Bourdon tube to measure the level of a liquid in a container. Again, as we did in bellows, the principle is very simple. When we have a certain liquid in a container and it is at a certain level, certain height above the reference position, the datum position. Sorry, it exerts a pressure because of its height, and that is given by the pressure of the liquid in the container is equal to rho g h. Rho is the density, g is acceleration due to gravity, h is the height. There are two conditions again. One is when the lid is closed, the tube or the container is closed. In that case only we have the liquid column pressure. In another case it is open, which is the most common case. It is the atmospheric pressure is also coming into play. So the total pressure here, okay, the total pressure here is the liquid pressure, liquid column pressure, and the atmospheric pressure. Okay, this. So this is measured by the sensing element. So we connect the Bourdon tube arrangement at the bottom. Okay, this fixed end connecting point is connected to the bottom of the liquid container. Okay, depending upon the size of the tube. This is only for small size tubes, okay, because the Bourdon tubes comes to a very small size. So this is for very small size tubes and containers. So it is connected to that point. As a result of the atmospheric pressure and the liquid column pressure, the Bourdon tube, it measures the total pressure, okay, which is the liquid column and the atmospheric pressure. The atmospheric pressure is, we get that detail, it is a constant value, so we subtract it from the total pressure, that is the sensor pressure. The pressure measured by the Bourdon tube, which is the total pressure here, okay, this is the total pressure which is measured by the sensor, the Bourdon tube, the liquid column pressure and the atmospheric pressure. So we subtract the atmospheric pressure from the total pressure, which is measured by the sensor, which gives us the liquid column pressure. That is equal to rho g h. Here there is an important condition, which is same as in bellows. The density of the liquid in the container, it should be known. Okay, it should be known. Only then we can measure the height of the liquid column using this, that is PL by rho g, because acceleration due to gravity, that is known, 9 point. Again depending upon the location it varies, but it is known. Density should be known. Liquid column pressure we get from this, okay, subtracting the atmospheric pressure from the sensor output, the sensor measured pressure, and then we get PL by rho g, that gives us the height of the liquid column. Now in case the lid is closed, this atmospheric pressure, that becomes 0 because it does not get involved in the whole thing. So simply the sensor pressure, it gives us the liquid column pressure directly. But if it is exposed to the atmosphere, we have to subtract it from the sensor output to get the liquid column pressure. Okay, so this is the basic principle of level measurement of a liquid in a container using Bourdon tube pressure gauge. So let us try to understand this whole thing from a three-dimensional perspective. So again, we have a container or a tube, whatever it is, where we have a liquid, okay, at a certain height. So when the liquid level it changes, this causes a change in the pressure exerted by the liquid column. Okay, so here when the liquid column causes a change in the pressure, the Bourdon tube, the fixed end which is connected to the bottom of the tube, that causes a change in the differential pressure, that is the pressure inside the tube and the outside, and that causes this blue end, okay, this blue end of the tube to rotate. Okay, this rotates, okay, along with this rod, okay, it rotates, it's free to rotate. Okay, so when this rotates, as a result of this secondary electrical transducer, which is connected to this rod, that either undergoes angular movement or linear movement through suitable arrangements. So it can be connected, as I said, to LVDT, capacitive, inductive, resistive, potentiometer, magnetostrictive, whatever it is. Okay, electricity, that is current based, through charge, electrostatic based or magnetostatic based, whatever it is. So that gives us a proper voltage or current signal. So there should be proper calibration also, which gives us a proper relationship between the linear displacement in meters or angular displacement in degrees into a suitable voltage in volts or currents in amperes. So there should be a proper calibration, that is, this much meters is corresponding to this much volts, or this much degree is corresponding to this much amperes. So that proper calibration should also be there. Okay, so this is the basic principle of liquid level measurement using Bourdon tube, and in most cases this whole arrangement comes in the form of a encapsulation or box to protect it from wear and tear. Okay, so this is the thing, that is liquid level measurement using Bourdon tube pressure